Hey guys, today we're going to learn about limits that involve infinity. So either limits that are going to equal to some infinity or limits as x is approaching positive or negative infinity. Now these particular limits are used to prove the existence of asymptotes. So let's first start with vertical asymptotes. Now on this graph we have the function f of x is equal to 2x plus 1 over x minus 3. As a reminder, we have vertical asymptotes whenever the denominator is equal to 0. If we look at this denominator and we make it equal to 0, we would get that x is equal to 3, because we would have to add the 3 to the other side. This means that there is a vertical asymptote at x is equal to 3. Now, even though we don't see it here, at the line x equals 3, we can tell that there is a vertical asymptote. So if I were to evaluate for these limits, the limit as x is approaching 3 from the left is equal to negative infinity. And the limit as x approaches 3 from the right is equal to positive infinity. Either of these limits would be used to prove that we have a vertical asymptote. Now let's look at horizontal asymptotes. If we look here, even though we don't see the line, we can see how the graph is leveling out on either side. This means that we have a horizontal asymptote at the line y is equal to 2. Now, if I were to evaluate for the limits here on the bottom, we have the limit as x approaches negative infinity of my function f of x. If I look on the left side, the limit is equal to 2. If I look at the limit as x approaches infinity, which is the right side, the limit is also equal to 2. So if we have limits that are approaching some infinity and it equals to a real number, these are the limits that we would use to prove the existence of a horizontal asymptote. So to put this together, an infinite limit is when you have the limit as x approaches some number c, whether it's from the left or the right, and if that limit is equal to either positive infinity or negative infinity, then that means that we have a vertical asymptote at that x value that the x is approaching. However, if our limit is where x is approaching either positive infinity or negative infinity, and that limit is equal to some real number, in this case d, then that means we have a horizontal asymptote at that particular y value. So let's review. Here we're going to evaluate for these limits. Now we've done these before, but now we're going to use these particular limits to prove to use as proof of some sort of asymptote. So in order to figure out these limits, if I were to, let's say with this first one, if I plug in the 2, I would get 0 in the denominator. So remember our different methods for evaluating limits. We have a rational function, so we're going to attempt to factor. Now in the numerator, I notice every number is divisible by 2, so I'm going to factor out a 2, which would give me x squared minus x minus 6 over x squared minus 4, which is a difference of squares, so that would give us x plus 2, x minus 2. Now let's just finish factoring the numerator. We have 2. X squared minus x minus 6 can be factored as x minus 3, x plus 2, over x plus 2, x minus 2. So here we can cancel out the x plus 2's, and I'm left with a simplified rational function of 2x minus 3 over x minus 2. Now notice here that the limit is for as x is approaching 2 from the left. So because this is a one-sided limit, we're going to want to plug in a number that is slightly to the left of 2. So I'm going to plug in 1.9. And remember, we're just taking note of the sign. So this would be 2, 1.9 minus 3 over 1.9 minus 2. Now 1.9 minus 3 would give us a negative number, over 1.9 minus 2, which is also a negative number. And a negative divided by a negative would give us a positive. So here this would be positive infinity. Before we go on to this next one, what this means is that this limit proves the existence of a vertical asymptote, simply because we have the limit as x is approaching a real number. And if you think about it, right, vertical asymptotes are written as x equals to some number. So if we end up with x is approaching that number and we end up with an answer as infinity or negative infinity, then that must have meant that we have a vertical asymptote there. So we would say there is a vertical asymptote at x is equal to 2. And the reason would be because the limit as x is approaching 2, in this case we did the left, of 2x squared minus 2x minus 12 over x squared minus 4 is equal to positive infinity. So the whole purpose of today's lesson is that we're proving the existence of vertical and horizontal asymptotes by using the limits and what they equal to. So your reasoning always goes back to our proofs here, what these limits are equal to. So if we're proving a vertical asymptote, we're going to use either of these limits. You don't have to do both. You only need one. And same thing for horizontal asymptotes. As x is approaching infinity or negative infinity, we only need one of those limits to prove the horizontal asymptote. So now let's look at this next one. We have the limit as x approaches negative 1 from the right. So if I plug in negative 1, I would end up with 0 in the denominator, meaning that we may have a vertical asymptote if that factor does not cancel. So we're going to factor both the numerator and the denominator. X squared minus 3x plus 2 can be factored to be x minus 2 and x minus 1. Over, now the denominator, I can factor out a 2 and I get x plus 1. Nothing ended up canceling here. So I'm going to have to plug in a number slightly to the right of negative 1. So I'm going to plug in negative 0.9. If we do negative 0.9 minus 2 and then negative 0.9 minus 1 over 2 times negative 0.9 plus 1. This would give me negative 0.9 minus 2, a negative, negative 0.9 minus 1, a negative, 2 is positive, and then negative 0.9 plus 1 is positive. So a negative times a negative is positive, divided by positive gives me the answer of positive infinity. So here we would say we have a vertical asymptote at x is equal to negative 1 because, and then we would restate our limit because this limit proves that we have a vertical asymptote. So because the limit as x approaches negative 1 from the right of x squared minus 3x plus 2 over 2x plus 2 is equal to infinity. Now let's look at this question here. For the function below, find any vertical asymptotes that exist. And then we're going to justify the answer using limits. So first I need to figure out where do we have a vertical asymptote, which occurs when the denominator is equal to 0, as long as that particular factor didn't cancel with the numerator. So we're going to factor everything, the numerator and the denominator. And here I have the steps for you to follow in case you need a review on how to find vertical asymptotes. So like I said, that first step is to factor the rational function completely. So let's go ahead and factor. In the numerator, I notice that I can factor out a negative 3. And when I do that, I get x squared minus 4x minus 12 over x squared minus 11x plus 30 can be factored as x minus 6, x minus 5. We need to finish factoring the numerator, which would be negative 3, and then x squared minus 4x minus 12 can be factored as x minus 6, x plus 2, over x minus 6, x minus 5. So now for step 2, we're going to see which factors cancel from the numerator and denominator, which in this case is the x minus 6. The factors that do not cancel from the denominator are the vertical asymptotes of the function when you set the factor equal to 0. So the only factor we have left in the denominator is x minus 5. So that means that our vertical asymptotes are going to be located when x minus 5 is equal to 0, which if we solve for x would be at x is equal to 5. So this is my vertical asymptote. But now we need to prove that this is a vertical asymptote. In order to prove that, we have to do the limit as x approaches 5 from either the left or the right. It does not matter which direction you choose. I'm going to choose the left. So let's see how my function ended up. My simplified rational function ended up being negative 3 over x plus 2 over x minus 5. So what I'm going to do now is I'm going to plug in a number slightly to the left of 5. And that is going to be negative 3. I'm going to use 4.9. So 4.9 plus 2 over 4.9 minus 5. So we have this negative 3. 4.9 plus 2 will be a positive number, and 4.9 minus 5 would be a negative number. A negative times a positive would give me a negative, and a negative divided by a negative would give me a positive infinity. So how I would write my final answer. There is a vertical asymptote at x is equal to 5, and now our reason would be our limit, because the limit as x approaches 5 from the left of f of x equals to infinity. Now again, I chose the left, but you could have chosen the right. That does not matter. Now, we're going to start looking at limits as x approaches either infinity or positive or negative infinity. First, we're going to start with polynomial functions, which a polynomial type function is anytime you just have terms added or subtracted with each other. You won't see any radicals and you won't see any rational parts, so meaning no fractions. Now, if your polynomial has n degree and an leading coefficient, so n is always the degree, which is the highest exponent of your polynomial, and where you see an, it says leading coefficient. It is the number that is attached to the variable with the highest exponent. So a little trick here is the degree or the sign of the leading coefficient will tell you what the right side of the graph is doing. What we're going to do now is we're going to determine end behavior, which is what your graphs are doing at the end. So either the left side of the graph or the right side of the graph. So the sign always tells you what the right side of the graph is doing. Then your exponent, the leading exponent, the degree, will tell you what the left side is doing. If the exponent is an odd number, it will be the opposite of the right side. If the exponent is an even number, then it is the same as the right side. So let's look at this first example just so you can get an idea. Here, if n is odd, meaning your degree is an odd number. So let's just say here x to the 5th is my leading term. Then the sign here tells me the right side, which this is considered to be positive. So you see how the right side is going up. And since the exponent is an odd number, that means that the left side is going to go in the opposite direction, so down. So the limit as x approaches negative infinity, which is the left side, would be negative infinity. And the limit as x approaches positive infinity, it's going up, so positive infinity. Now, if your degree is still an odd number, but your leading coefficient is negative, then let's say this is negative x to the 5th. You see how we have that negative? That's going to tell me the right side of the graph. So you can see the right side is going down. And since the exponent is positive, the exponent is odd, that means that the left side is going up, because it's always got to be the opposite. So the limit as x approaches negative infinity, the left side is going up, and the limit as x approaches positive infinity, the right side is going down. Now, if your leading term has an even exponent, then whatever the sign is of the leading coefficient will tell you both sides, because an even exponent means that the left side and the right side are going to go in the same direction. So here we have this particular graph. Let's just say it is x to the fourth. So you see how this is positive, the right side is going up, and the left side is going to also go up because my exponent is an even number. So the limit as x approaches negative infinity and positive infinity would both equal to positive infinity. Now this one, you see how both ends are going down. Let's say the leading term is negative x to the fourth. Then because this is an even exponent, both sides are going in the same direction. And since this is negative, that means both sides are going to go down to negative infinity. So now this is called the leading term test, which is how we determine the limits as x is approaching some sort of infinity of polynomial type functions. So to kind of summarize what we looked at in the previous slide, the sign of the leading coefficient will tell you the right side of the graph. If the exponent of the leading term is odd, the left side will go in the opposite direction, and if the exponent of the leading term is even, the left side will go in the same direction. Now what I do and what I recommend you do is to draw arrows to represent your end behavior to help you in your analysis. So if I look here, we have 2x to the fourth minus x squared minus 8x. My leading term is the one that has the highest exponent, which is typically written in the front of the polynomial if it's written in standard form. However, you always want to scan the polynomial in case the order is mixed. So this is my leading term. So I notice that my leading coefficient is positive, so that means that my right side is going up. And since my exponent here is an even number, that means that the left side is also going up. So I draw arrows in the order of which I just spoke, right? So this is the left side and this is the right side. So the left arrow, the right arrow represents my end behavior. So if I look here at my limit as x is approaching positive infinity, we are talking about the right side of the graph. And since the right arrow is pointing up, that means that this limit is equal to infinity. Now in this example, we have the limit as x is approaching negative infinity, and we have the polynomial negative 6x squared plus 3x minus 2. My leading term is the negative 6x squared. Because it's got a negative coefficient, that means that the right side is going down. And because the exponent is even, that means that the left side is also going down. Now I look at my limit. It says as x is approaching negative infinity. Here we are talking about the left arrow. And since my left arrow is pointing down, that means that this limit is equal to negative infinity. In this next one, we have the limit as x is approaching negative infinity of 2x to the fifth plus 2x to the third minus x squared plus 8. My leading term, again, always the one with the highest exponent, which is 2x to the fifth. Since this is positive, that means that my right side is going up. And since the exponent is an odd number, that means that the left side is going to go in the opposite direction. Now, since this limit is for as x is approaching negative infinity, that means that we are talking about the left side of the graph. And since my left arrow is pointing down, that means that this limit is equal to negative infinity. Last example here, we have the limit as x is approaching positive infinity of negative 3x to the third plus x minus 4. So since my leading term here is the negative 3x to the third, and I see that the leading coefficient is negative, that means that my right side is going to go down. And since the exponent is odd, that means that the left side is going to go in the opposite direction, so up. Now, when I look at what the limit is approaching, it says approaching positive infinity. We're talking about the right arrow. And since my right arrow is pointing down, that means that this limit is equal to negative infinity. Now let's have a look when we're evaluating for these kinds of limits of rational functions. Here you are given some graphs along with their equations. So we're going to, for now, use the graphs to find these limits. And then I'll show you how you use the equation if you're not given a graph in order to find out these limits as x approaches either infinity or negative infinity. So let's start with the limit as x is approaching infinity of this function. Positive infinity, right side of the graph, we see that it's leveling out at 1, and that's because of that horizontal asymptote. So remember that we use these limits to prove that we have a horizontal asymptote. Next, we have the limit as x is approaching negative infinity, which we can see is leveling out at the line y is equal to 0. So this is going to equal to 0. In this one, we have the limit as x is approaching positive infinity. So we look at the right side of the graph and we see that it is going up. So this would be infinity. So if we end up with a limit as x is approaching either infinity or negative infinity, and our answer is another infinity, that means that we cannot state that there is a horizontal asymptote. Now, in this last one, we have the limit as x is approaching negative infinity. So the left side of the graph, we see it's leveling out at the line y is equal to 2. So now how do we find these limits if we're not given the graphs? And that all depends on whether we have a horizontal asymptote. To figure out if we have a horizontal asymptote, what we do is we compare the degree of the numerator with the degree of the denominator, meaning we're looking at the highest exponent of x in the numerator with the highest exponent of x in the denominator. So in the first example, we have the limit as x is approaching infinity of 2x plus 1 over x minus 3. If you notice, the degree of the numerator is 1, and the degree of the denominator is also 1. If the degrees are equal, that means that we have a horizontal asymptote where the coefficients are attached and we divide them. So we have 2 here over 1. We basically ignore the rest of the rational function. We just look at the leading terms of the numerator and the denominator, and we're going to divide those coefficients. 2 divided by 1 is 2. So that means that we have a horizontal asymptote at y is equal to 2. In this next one, if the degree of the numerator is higher, then that means that the limit is going to equal to infinity or negative infinity. I have here infinity as just an option, but it could also equal to negative infinity. So how would we determine that? What this means is that this particular function does not have a horizontal asymptote. So if x is approaching infinity, what I do is I kind of think about plugging in infinity and see what sign I would get. If you have infinity squared, that's going to be positive infinity. Over infinity, they're both positive, so the answer here would be infinity. And this means that there is no horizontal asymptote. Since remember, the limit as x is approaching either infinity or negative infinity, it has to equal to a real number to prove that there's a horizontal asymptote. If it equals to infinity or negative infinity, then there is no horizontal asymptote. Finally, if the degree of the denominator is higher, that means that the exponent is higher in the denominator, then that means that we always have a horizontal asymptote at y is equal to 0. So that limit is going to equal to 0, and we have a horizontal at y equals 0. And below all of these explanations here, all of these limits, I have an explanation as to why this is true. If the degree in the numerator is larger, then that means that the numerator is going to get larger at a much faster rate than the denominator. So the function value is only growing and getting closer to infinity or negative infinity, meaning that there is no horizontal line blocking that function. Whereas if the denominator is growing at a much faster rate than the numerator, then we're getting smaller and smaller fractions, which smaller and smaller fractions keep approaching 0. So let's try that. Here we have the limit as x is approaching infinity of 5 minus 2x minus 2x squared over 3x squared plus 2x minus 3. So what we're going to do is we're going to pull the highest exponent or the leading term of the numerator and the denominator. So here the leading term in my numerator is the negative 2x squared, and the leading term of the denominator is 3x squared. Since they have the same degree, then we take their leading coefficients and we divide them. So this is going to equal to negative 2 in the numerator over 3, which if I could simplify that, I would, but I can't simplify. So this is my horizontal asymptote because this limit is equal to a number. So before we move on to this next one, this limit proves the existence of a horizontal asymptote. So that means that there is a horizontal asymptote at y is equal to negative 2 over 3. And now here I would state the limit because the limit as x is approaching infinity of 5 minus 2x minus 2x squared over 3x squared plus 2x minus 3 is equal to negative 2 over 3. Now in this second example, we have the limit as x is approaching infinity of x squared plus 3x minus 4 over x minus 5. So we're going to pull our leading terms from the numerator and the denominator. In the numerator, my leading term is x squared, and in the denominator, it's x. Since the degree of the numerator is larger than the degree of the denominator, then this means that we don't have a horizontal asymptote because of that higher degree in the top. So we're going to actually evaluate what this limit is equal to. If I take the infinity squared is positive, over infinity, another positive, we end up with positive infinity. So here we would state there is no horizontal asymptote because, and now we state our limit. The limit as x approaches infinity of x squared plus 3x minus 4 over x minus 5 is equal to infinity. So now what we're going to do is we're going to put all of this together. With both of these functions, we're going to find the equations of the vertical and horizontal asymptotes, and then we're going to justify the answer using limits. So let's review vertical asymptotes again. In order to find the vertical asymptotes, we have to factor everything. So for f of x, I notice that in the numerator, I can take out a 3 from every term. So I'm going to factor out a 3, and that would give me x squared minus 7x minus 8 over, then x squared minus 5x minus 24 can be factored as x minus 8, x plus 3. The numerator can be further factored, so I'm going to take out the 3, and this can be factored as x minus 8, x plus 1, over x minus 8, x plus 3. I can cancel out the 8's, and I get that f of x is equal to 3 times x plus 1 over x plus 3. Since I still have a factor left in the denominator, this means that I have a vertical asymptote when that factor is equal to 0, which is at x is equal to negative 3. But again, I need to prove this. So in order to prove we have this vertical asymptote, we have to find the limit. And we would do the limit as x is approaching -3, and you can choose from either the left or the right. I did the left earlier, so I'm going to do the right. So this is my function here. This is f of x now that it's simplified. So I am going to plug in a number slightly to the right of -3, which would be -2.9. So we would have 3 times -2.9 plus 1 over -2.9 plus 3. In the numerator, I have the 3, which is positive. -2.9 plus 1 is negative, over -2.9 plus 3, which is positive. A positive times a negative is negative, divided by a positive gives me negative infinity. So here we would state, there is a vertical asymptote at x is equal to -3 because the limit as x approaches -3 from the right of f of x is equal to negative infinity. Now to figure out if we have a horizontal asymptote, we compare the degree from the numerator with the degree of the denominator. These are my leading terms. Since they have the same degree, we take the leading coefficients and divide it. This is 3 over 1, so that means that I have a horizontal asymptote at 3. So we would say there is a horizontal asymptote at y is equal to 3 because, and then we would state our limit. If we have a horizontal asymptote, the limit from the left, or rather the limit as x approaches infinity and the limit as x approaches negative infinity would equal to that value. So you can choose which side you want to write. So I'm just going to use positive infinity of f of x is going to equal to the value of my horizontal, which is 3. Now let's look at this last one here. We have g of x is equal to x squared plus 5x over x squared plus 4x minus 5. So to figure out my vertical asymptotes, we need to make sure that everything is factored. So let's factor this out. In the numerator, I can factor out an x, which would give me x plus 5. In the denominator, x squared plus 4x minus 5 can be factored as x plus 5, x minus 1. My x plus 5's cancel, and I'm left with my rational function of x over x minus 1. This means that I have a vertical asymptote when my denominator, x minus 1, is equal to 0, which would mean that it is located at x is equal to 1. So now that I know where my vertical asymptote is, I need to justify this using limits. So let's do the limit. As x is approaching that number, 1, and you can choose the left or the right. I did the right here, so let's do the left of g of x. And now I'm going to plug in a number slightly to the left of 1, which would be 0.9. Now 0.9 is positive, and 0.9 minus 1 is negative, so positive over negative would give me negative infinity. So now let's put this into a statement. So there is a vertical asymptote at x is equal to 1 because, and now we state our limit. The limit as x is approaching 1 from the left of g of x is equal to negative infinity. Now to check for horizontal asymptotes. We check the degree of the numerator with the degree of the denominator. Since they are the same, we divide their coefficients. Even though we don't see it, there's a 1 here and a 1 here, and 1 divided by 1 is 1. So that means there is a horizontal asymptote at y is equal to 1 because, and now we state our limit. I always just use the limit from the right. The limit as x approaches infinity of f of x is going to equal to that value, which is 1. Now the last thing we're going to look at is what if our limits are approaching negative infinity of these rational functions. Now what we would do here is the exact same thing as x is approaching positive infinity. The only time that you ever have to worry about the limit as x is approaching negative infinity is if you end up with a case that there is no horizontal asymptote. And if that's the case, we need to figure out our answer, whether it is positive infinity or negative infinity. So I have the graphs here for these examples so that you can compare your answer. So for this first one, we have the limit as x is approaching negative infinity of 2x squared plus 7x plus 6 over x squared plus 5x plus 6. Since the degrees are equal, then I can just take their coefficients and divide them. So notice I'm not doing anything different. The limit as x is approaching infinity and negative infinity, as long as there's a horizontal asymptote, is always going to equal to the same number, which in this case is 2. If you had a higher degree in the denominator, then that means that there's a horizontal asymptote at 0, so you would put 0. However, look at this one. We had the limit as x is approaching negative infinity of x squared plus 3x plus 2 over x minus 1. So because the degree of the numerator is higher than the denominator, this automatically means that there is no horizontal asymptote. And if there's no horizontal asymptote, then we don't exactly know what our end behavior is doing, whether it's going down or up. So what I kind of do, and I put it here in this bullet point, take the leading term of the numerator and denominator and think about plugging in infinity and evaluate by using what you know about even and odd exponents to determine the sign of the infinity. So in the numerator, my leading term is x squared, and in the denominator, my leading term is x. So let's plug in negative infinity. Negative infinity squared is going to give you positive infinity, since anything squared or anything raised to an even exponent will be positive. And then in the denominator, we have negative infinity. So a positive divided by a negative would give me an answer of negative infinity. And if you look on the left side of the graph, we see that it's going down, which is negative infinity. So when you have a limit as x is approaching negative infinity of a rational function, where you end up with no horizontal asymptote, just kind of plug in the infinity and see what sign you would get. And that's limits involving infinity.